screen. So the next speaker will be the Professor Ibraheem Al-Naib, and he will with a very interesting talk on biosensing using Terahertz Metasurfaces. Please, when you are ready.
Okay. Good afternoon, good morning, good evening, wherever you are. I'd like in the beginning to thank the organizers for this kind of invitation. Thank you very much. So as you see here, we are going to talk about using Terahertz Metasurfaces. And here is, if it happens that you are coming by the Imam, it will be very, of course, nice to show you around. This is the campus of the university, and this is the College of Engineering that we have. It's a new campus, very nice place on the beach. Good, so here is the outline. After a very brief introduction to Terahertz applications, we will talk about the importance and challenges of biosensing and why to use Terahertz and utilize the metasurfaces. Then some primitive results using biosensing Terahertz Metasurfaces, and then finally with a short summary. So as you see here, scientists have been utilizing terahertz waves in the last 20 years now plus in different applications: non-destructive testing, environmental monitoring, security and defense, solar energy systems, future wireless communication, the next 6G. And last is actually the biomedical imaging and sensing. So today we are going to talk about this part here only, but terahertz can extend to many other applications. So the importance here, I think it's important to mention about are being used in the medical field to do what? To diagnose infectious diseases, gene therapy, and you can find books actually showing different techniques and methods for biosensing, which is very nice actually. Drug discovery, cancer diagnosis and monitoring. So it looks pretty interesting actually, even with determining effectiveness of anti-cancer chemotherapy agents. Good, so it looks pretty nice topic. Nevertheless, there is nothing ideal in the life, so we have many challenges here. The challenges when you use different techniques that rely on labeling. So the target is basically like some dyes that may change original properties of the target, and also some techniques rely on invasive methods. So luckily, we have the optical techniques that can be label-free and non-invasive. But the problem is the high photon energy that we have with the optical wavelengths that change again the target properties. Also, with many biosensors, they have field confinement, which is a problem, as you will see, and hence low light matter interaction that lead to low sensitivity. So we need to work with, actually here, I'm trying to motivate for the terahertz because they are low, they have low energy, as you know, it's milli-electron volt. And we will talk about metamaterials that can confine the field. That's why we have the terahertz to address these two challenges. Right. So what we need to have is to have label-free characteristic, use low photon energy, use a small quantity, perhaps even less than a femtomole. The spectral response should be feature a high quality factor, very sharp. The field should be confined in areas, and hopefully with these two conditions, we will get the sensitivity that we want. That is not the end of the characteristic. We need to do it in real time and in vivo, which is really maybe the next challenge that we need to work on. We have a long list of things here. And finally, to detect the dynamic modifications as things happen over time. So what is going on? Right, so let's start some of the fundamental questions that we have when it comes to biosensing. Now, we said terahertz low photon energy, but normally the sample, imagine a single-stranded or double-stranded DNA that you extract. The amount of that material will be rather small. So for only a very short interaction then length in conventional spectroscopy configuration. So you are talking about sample in tens of or maximum hundreds of nanometers. And the wavelength is the ruler, right? We use at 1 terahertz is 300 micron. So what we are trying actually is kind of analogy is something like that. It may look funny, but it is actually very optimistic here analogy. The real case is even worse. So then we need to confine this field. We need the electromagnetic field should be confined to increase the interaction under test. So we need to do something in order to have things comparable. And this comes here into play, the materials. I like very much this pictorial, basically three different kind of metamaterials is maybe kind of old now, but still it's actually gives inspiration here. And for me, most importantly, that the roots of all this are the micro frequency selective surfaces. So many scientists have been trying to build very nice 3D, complicated, very sophisticated metamaterials. Of the day, they are very nice, but it is difficult to fabricate them, and they are not well matched to free. So if we can do something with an easier fabrication method, why not to achieve the goal that we have? And here surfaces and the different designs that we can work with. So when it comes to simple splittering resonator, if we look at a field here, spatial electric field, we see nice confinement of the gap. This could go to 5, 10, or even maybe 30 times the field compared to source. So it has really a potential then for sensing application. And this is how the story started with the here some basic physics about this splittering resonator. This is here the dispersion diagram. So if the electric field is here 90 degrees perpendicular to the gap, we have very wide band, and this corresponding to very broad band. And we call this with n equal 2 because we have two nodes with the current distribution in phase here. That's why it's well coupled to free space. We have low quality factor and confinement. Now, if this by 90 degrees like this, we will get two, as you see here, this is one, and this is the second band gap with the green here, and two, of course, bands with in transmission, and we refer to this as LC, inductive capacitive resonance, with only one node that we have. That's why it has better sharpness. And then we have also the quadruple mode with when we have three nodes basically in here. This is a very short list of many groups around the world worked with this, not necessarily, of course, a full list. Many people, including many presenters in this nice seminar that utilize this SRR. So it was very nice actually to start from this. I think here, I think it was a book chapter in 2003 suggested theoretically working with Fano resonators and then applied in this at microwave frequencies that, okay, if we take this symmetrical SRR, something like the rate basically response, this is here the measured, simulated, with the here horizontal and here is vertical. Now, if we break the symmetry of this SRR, we have just different lengths of these two arms. We start to get this asymmetric Fano-like resonance, which is much sharper than a conventional dipolar one. If we go with the other polarization of this will disappear and prove that experimentally compared to the simulation. Here you see the sharpness in the simulation is more, because here normally in the measurements we are limited with the TDS, how long you can scan, depends on the thickness of the substrate that you have. If you look at the current distribution, you see that at Fano resonance the anti-phase, so things look like they go, of course, depends on the phase, counterclockwise. That's why it's less coupled to free space, and it has this very nice high quality factor. At dipolar mode, it's in phase current distribution you get. The current is, of course, much less than in here. So the field is confined much better around the here. Right, so with this idea, of course, it opens the door to many other structures. This is here, very similar one, but you have two resonators in the unit cell instead of only one. And here is a nice comparison between green one, the complete symmetric structure. Then if you break the symmetry, for example, the asymmetric one like this, and you go with the two resonators, you get even much sharper resonance. And this is all proved experimentally, of course. So here is how instead of only one anti-phase current, we have two, and they cancel each other in a better way. That's why we get this nice response. You can, using the same here resonator, but instead of moving the two gaps to the right, you move only one of them. The other one is still in the middle. And if you take the electric field now parallel instead of perpendicular, you get what we call the electromagnetic induced transparency. So if the gap this here is not moved, you get the black response here, black curve. And once you move this gap, you start to get very nice peak here in the middle. So the electromagnetic induced transparency here. And you can still use the other polarization and you get the Fano resonance. This is what has been done here with simply photoresist, depositing photoresist on the top as analyte, just to show the sensing ability of this structure. So you see that here with Q factor of, and here is 65 with the quadruple mode, but not necessarily that with higher quality factor you get better. It depends on many things. It turns out that it depends on the substrate thickness. We did analysis for that. Then it depends also on the analyte thickness. So if you here take the substrate micrometer, you change the analyte thickness, you see the sensitivity here. changes, and then obviously saturate at certain thickness. After, of course, you are changing the capacitance in the environment. So almost after 8 micrometer of analyte, things will and you are not interested even in very thick samples at the end. Now, if you to 1 micron and you start to change the substrate thickness, you decrease it here, you start to get better. And this comes here to the question, what is the universal definition of activity? It is, if you read in the literature, you find difficulty. Different papers talk about different definitions, but if we would like really to put things into context here, we should take the frequency, resonance frequency, the analyte thickness, the substrate thickness, the shift of the, or sometimes even the amplitude, as we will see. So all that should be put in one definition. What you can do also with, actually, you can take silicon on sapphire. So you remove the silicon here from around the split ring resonators and leave it under the resonator, and then you do the lithography for the metal here, which is aluminum. So you have aluminum and then sapphire. Then you send your terahertz wave with also optical pump, and the silicon here, of course, will then conducting, right? So what happens in, this is the experimental work, the simulation with collaboration with Professor Ranjan Singh group from Singapore. You can turn off this electromagnetic induced transparency completely, basically. So as you see here with 40 milliwatt. And the nice thing about this structure, you can use much less power compared to other tunable metamaterials that will need maybe 1 order of magnitude more optical power to do the same here. Also, you can extend the work to work with a supercell instead of only 1 unit cell. And here it shows the work with 4 resonators with the gap here shifted. And in the second one, you see them mirrored. So we mirror this around y-axis and mirror it again around x-axis. So we get these 4 gaps to be closer, if you like, and you achieve much better sharpness due to the antiphase, current in a similar way, but at the supercell level. In the beginning, the difficulty with having sharp mode with even mode or n equal 2 when we have 2 nodes, but it turns out that we can solve that problem by having 4 of these completely symmetric resonators, but we turn 4 resonators around the middle point here with different angles, and we can very high Q factor in the case here around 1 terahertz. And this is here, the ripples tells you that the scan time was not enough to get the sharpness as it shows in the simulation. Of course, you can go for these different polarization, you study them at angles, and you see as you increase the angle here to almost 9, you just start here, you get almost the same resonance sharpness. So people started to call this BIC, bounded state resonance, and it's basically the same effect. Another very nice structure that here completely symmetric structure. So you can say you have a library of different structures, and you can choose among these with different bases of the physics that you have. Here you can say, okay, I can break the symmetry here by adding a microstrip side and this side, and you start to see very small resonance. Once you connect these two resonators in each of the super conductively, so you get a very nice, much sharper resonance compared to the dipolar one, which makes things easy here compared to the asymmetric one, because any little change in the asymmetry will change the response. So here it's completely symmetric. It's much easier to come up with this just by connecting every two resonators to each other. And here it shows how the current can be really enhanced. Right, you can use that structure for biosensing, and for biosensing, of course, normally we cover the whole array, but if we look at the spatial electric field, we notice that the field is confined in around the gaps here. So why don't we just cover these two spots? Because we know that the amount of material will be much very small at the end. So we cover that just these 2 points, and still it turns out that we can compare here between the blue one, nothing on the top, then here the solid curve with the whole area is covered, and then the dashed dotted curve with only the two spots covered, and you see that you can still get a measurable shift that is well defined problem with that. So this will save a lot, maybe less than 5% from the material that you need to use. Not only that, but when it comes to completely symmetric structure, so what you can do actually, you can use the analyte itself to break the symmetry. Instead of breaking the symmetry of the structure, you use itself to break the symmetry. So if you do that actually with the uncoated one is the dotted curve here. Once you coat half of it, you are inducing now, the analyte is inducing this resonance, and depends on the thickness of this analyte, you can have different in a very nice way. And of course, all compared to no resonance, that is very easy then to kind of material that you have. Normally we have a problem with, we don't have a problem, as we said, with micrometer analyte thickness, but to very small thickness, then we have a problem with the shift in the resonance. Here 0.25 micron will show a very small shift, but what we can do is the difference between these two amplitude response, and we get this almost 6% difference that we can easily find out what kind of then thickness that we have. So if we take the difference in the amplitude, we can work with really very small thicknesses we call sub-micron. When we work with more than maybe 1 micron, it's very easy to take the difference, because here it's just saturated in the amplitude. Here it shows also the comparison when it comes to between 0.25 and 2 micron, and with the shift in the amplitude, and in the second part here. So even with 0.25 micron, we can show that. Experimentally, this has been shown to find, and they could show in this paper that even 7 nanometer of germanium was basically able to sense it, which is amazing result based on the fact that they used the amplitude difference from the proposal that we had in the previous slide. So when it comes to also electromagnetic induced transparency, normally they use 2 rings, one inside each other. And recent work here, what I try to do is just to take the inner one just outside, because in this case, you can have full control over the radius, because if it is inside, you are limited with the width and the gap between them. Here, you are free, you can make them the same, and you get the dashed response here. But once you have the second ring with just 5 micrometers smaller, you get very small, very sharp response as in here when it comes to transmission and reflection. And you can take just this part show that if you have better conductivity, you can even get much sharper response. Here, of course, is the ultimate goal. Value is T. Of course, that is not doable experimentally, but it's just to show the limit of the structure. And you can define the quality factor. Normally goes down to PEC and goal, and the amplitude here goes up as you increase the parameter. And if you multiply these both, we call this figure of merit. So there is optimum value here, which is almost, I think, 88 resonators, and it's extremely high for PEC, of course. What you can do here, actually, you can fabricate these structures not only lithography, you can build your own system using nanosecond laser, and just take from your kitchen some aluminum foil and have complementary resonators, and it works actually. And the performance of such is not too bad compared with the cost so you can use it for sensing. And the nice thing here, when it comes to complementary, we call it freestanding structure, it has much better, almost 3 times much more than 3 times actually, the sensitivity, that because there is no at all here. Right, you can use also aerosol jet printing here, and we with collaboration Calderwoe, we showed very simple design here using aerosol jet. This is very fast printing metamaterials. I would like also you to read this nice recent review. It's written in a very nice way, and I really like it. So we could say that we have an energy, sharp resonance, confined field, high sensitivity, but still we need to work towards having a quantity of in less than femtomole time, detect dynamic modifications. So we have a lot of work. I hope I could show you some examples here of high quality factor Terahertz metasurfaces, and these designs can be employed to realize high selective narrowband and most importantly, high sensitive Terahertz-based sensors. Of course, I have been taught with many people mentored me, and I supervised many others, collaborated with others. So I'm grateful for all of them. I would like to thank the organizers again, and thank you very much for your attention.
Thank you. Thank you for the really nice talk. And as I didn't see a question, I will ask one that I was curious about. So we are focusing now in the Terahertz region, and you are interested in biosensing. Will be a problem in the water? I mean, water is highly absorbing in that region. Will be that, I mean, even the water in air, I think, could be that a problem?
Yes, working with aqueous, let's say, samples, this is the goal at the end, because we don't like to take the sample, dry it, and because this, again, may change the properties.
Exactly.
So many groups working on that, and I think this is the real challenge. We need to be limited to the amount of we use, but we need to deal with small amounts anyway. So I think there is some room trade-off. Yeah. Very
okay.
nice, very important question.
Thank you for the really interesting talk.